Hi everybody. Let's go ahead and get started. Today we'll be doing a quick warm-up and then we'll be going over that second question from the free response. For your guys' homework, I posted online a video that I'd like y'all to watch an outline from the College Board. This one is about gravitation. That's all the homework you have for the weekend, just because it'll take about an hour and I don't want to like burden y'all with stuff because I know you have other classes to deal with as well. Just so you all know, next week we'll be doing a review of everything we need to know about energy and momentum. And then after that, the final review topic will be things that spin and things that go back and forth. And we'll be done with our review of the class for test at the beginning of next month. So for today, item number 1, a car's tires on average have a coefficient of friction mu. Now, of course, the coefficient of friction between a tire and the ground isn't constant. What are some things that would actually change mu? Which means that mu isn't truly a constant. It's actually a function, right? What things do you think go into determining mu? And this is an engineering question, not a physics question. I just, for the sake of your brain, what is this mu describing? What changes how sticky a car's tires are with respect to the ground? What are some of the changeable variables?
Grip.
What is that? That is what I'm describing.
Isn't it like how the surface is, like if it's rough or smooth?
Okay, so that's an actual thing that we can talk about. So road surface, right? So is it nice blacktop, or is it freshly poured blacktop for the sake of a track? Or is it crappy gray cement that's all beat to death, right? Different types of road will have different types of grip against your tires. What else?
If there's liquid, I don't know.
Like
The weather.
weather, yeah.
If the road is wet or if the road is snowy, you will have less grip, and as a result, it will make mu smaller. What else? There's one other obvious one.
What about
The
like
tires.
the type of tire?
The type of tires, and now let's talk about some of the specific properties of the tires, right? Because friction is the interaction of two surfaces. So basically, these first two parameters describe the bottom surface, which in this case is the road. But in terms of how much grip you get from your tires, what is the style of tire? Is it a regular old tire? Or is it some sort of racing tire that is designed with a specific purpose in mind? What are some other features of a tire that could affect how much grip you have?
How much air pressure?
That's a big one, the amount of pressure that they have, which is why it's really important that you periodically check your tire pressure if your car doesn't have the digital thing that checks it all the time, and it'll give you a little warning of low tire pressure. Having low tire pressure can be really bad for you in a bunch of ways. Not only will it make it more dangerous to drive, but it's also a waste of gasoline because you'll have worse mileage. Next time you drive, whenever that is, check your tire pressure and make sure that it's the recommended amount. The other thing that could affect this, The other thing that can affect this is the amount of tire tread left over. So basically on the bottom of your tires, they have these teeth. And the more you drive, the shorter and shorter and shorter and shorter and shorter the teeth get. The shorter they are, the less grip you have against the road, and the smaller it makes your coefficient of friction. Though when we do physics, right, we're not doing engineering. So we're going to eliminate all of these realistic variables and just say it's a single number mu, with the knowledge that mu can be changed by these real life things. And so what kind of question is this asking about? A car takes a turn. So what kinds of variables are we going to have to put on here?
Mu.
Mu, which is the amount of friction that the car has with the ground. And is this a linear pathway or what?
Circular.
Yeah.
Circular. So I'll have to go ahead and define a radius of curvature. So this is R. What else do we need to throw on here?
Acceleration.
Yeah, there has to be some central words acceleration. Otherwise, we can't move in a circular fashion. So at every point, there will be some acceleration pointed towards the middle coming from our friction. And the thing that we're solving for is the velocity. So what is the speed limit? How fast can we go without it being a problem? And so we could get into talking about the free body diagram for the car. It would be 3D though, and it would be 3 forces. Number 1, down, the car has a weight. Number 2, up, the car has a normal force coming from the ground. And it's going to have a force to the right, in this case, acting on it. That's the friction from the tires. That's what's going to cause it to turn right. However, in this case, that friction is going to act as what type of force? The friction from the tires is going to act as a centripetal force leading to this circular motion, this change in direction, which is to say that centripetal force is equal to the friction. So we're going to set those two equations equal, and then we're going to solve for V. So what is the equation for friction? How much friction does an object experience on a flat surface? Force due to friction equation?
mg.
That's weight.
Isn't it normal force times mu?
It is mu times normal force. And if you're sitting on a ramp, the normal force will have a cosine in it. But since this car is sitting on a flat surface, since it's unbanked, this is just going to be equal to mu mg. So this right here is the this right here is the force due to friction acting on the tires. And this is acting as our centripetal force. So this should be equal to what? What is the centripetal force equation?
mv squared over r.
mv squared over r. So if we want to know what is going to be the posted speed limit for this particular turn, we're going to take this and we're going to solve it for v. Step 1, divide both sides by m, which shows that the mass is irrelevant. This is why speed limit signs don't have like, hey, for light cars, it's this speed. For medium cars, it's this speed. And for heavy cars, it's this speed. You just give one speed for everybody. And then number 2, we're going to multiply both sides by r. So it's mu times g times r is equal to v squared. And now we're going to take both sides and take the square root. So the speed limit that's posted is equal to the square root of mu g r. So here's what this is telling us. The larger that mu is, the faster you can safely take a turn. If mu is bigger, if you have more grip with the road, you can make that turn faster without, drifting. And if the radius of the turn is bigger, that also allows you to go faster. If r is bigger, v is bigger, which is to say that the less, the looser a turn is, right? Because a tight turn is difficult to make. You have to slow way down almost to a stop to make it safely. The bigger the radius of curvature of the turn, the faster you can take that turn safely. That's why the loops to get on the freeway are so big. That's item 1. Are there any questions there? No? Okay. Number 2, this is going to be posted shortly as an assignment. I just wanted to talk about it now before it goes up over the weekend. I'm going to ask you to clean up your notebook and get it ready for storage. If any of y'all happen to go on to be scientists specifically, almost everybody keeps their lab notebooks over time and fills a shelf out with it. So your first lab notebook might as well be your first honest to goodness lab notebook. So if you plan on majoring in a science, please do clean your lab notebook up and get it ready to keep. Not to mention next year when you're freshmen in college, some of the college labs that you do may be the same as the ones that we did. I know that to be the case considering I've taught college labs, and some of the labs that we did I took from that same playbook. So maybe these will be coming in handy within the next year. But also, if the AP test were to happen to ask a lab design question of a lab that we've done before, which has happened to me, there was 2 years where one of the questions on the AP test was a straight up lab that we did in the class. And after I found it afterwards, I was like, haha, they knew that one. It definitely is good for you to go through your lab notebook and go back over the labs we did this year. and give them a once over just to refresh yourself on what it was we were doing and what it was we were measuring, especially those ones from the early part of the year. I basically guarantee now that you know more physics, right, you're smarter. If you go back and you look back at some of those earliest labs, like when we were measuring gravity with the ticker tape, back then it probably didn't make the most sense how that stuff worked out. But if you go back and look at it now, it'll make good sense. So update and complete for me the table of contents. Number all of the pages according to the documents that I gave out at the start of the year, which if you lost them, they're still on Google Classroom. Permanently attach any pages. So if you have loose pages in there with graphs or whatever on them, just affix them in place with a piece of tape, because you don't want to open it years from now and have that stuff come pouring out. And then finally, be sure to read over the comments that I wrote in by hand and any changes that you made, just because every single one of those is a mistake that you do not want to repeat on the actual AP test. I'm just going to ask you all to, when you're done with all of this, just submit proof in Google Classroom. Now, I'm not asking you to scan every page of your lab notebook because that's terrible for a bunch of reasons. One, that's a waste of your time. Two, I'm not going to grade that. I'm not going to look at all of that information. And three, that many files would just destroy my Google Drive. I would instantly go over the cap, right? So all I'm going to ask you to do is to give me a picture of the table of contents that's completed. Show me a few of the numbered pages. I'll probably just ask for like 3 samples of like, hey, show me some of the high numbered pages that you got to. And that will be all that I ask you to turn in for that particular assignment. Are there any questions there about cleaning up and preparing your lab notebook for storage?
We just like send a video of us flipping through it, or would that take up too much space too?
That's fine. That's probably overkill, but yeah, that's fine if you want to prove that your lab notebook's done and ready for storage.
Okay.
I just regret that of all the stuff that I like grabbed out of my classroom before we got sent home for the great quarantine of 2020, that I didn't also grab my sample lab notebooks.
Oh.
Yeah, that's a bummer. Yeah, which like now I need to go back and get them even after the school closes, which sucks. I have to go back and grab that stuff because I'm not going to leave that stuff behind. I've been carrying around my AP Physics lab notebook since 2007. Hey, anyway, we're now going to go over the second part of the free response that I assigned to y'all, the Unit 3 one, and this one is about some planetary orbits. And first off, they're going to start talking about relative forces, and then down below they start talking about relative speeds. And this is a question of mathematical variation, which is a little bit of what I showed y'all down here, where we talk about, well, if I increase mu by some factor, it'll increase v by the square root of that factor. If I increase r by some factor, it'll increase v by the square root of that factor. That thing where you can look at an equation and you can instantly tell how changing one variable will change another variable, that is, as a skill in math, called mathematic variation. And that honestly is 90% of what scientists and engineers do. And it is the overwhelming majority of the conversations that we have with each other. It is the clearest way to talk about what equations are doing and why they're important. And it's also one of the clearest ways that you can figure out what an equation is based on real data. Look at a data table and be like, oh, these things are related quadratically. That thing goes up as a parabola. So there must be some sort of x squared somewhere in the equation between these variables. So let's go ahead and look at mathematic variation today, but in the very specific context of the planetary orbits that they laid down for us. So we have 3 different systems. They could be, and they are solar systems. Each one is planet star. But of course, that literally doesn't matter. The math of a planet orbiting a star, or a moon orbiting a planet, or even if you were somewhere out there in deep space and for some reason you had 2 tiny, tiny pebbles, even those 2 tiny, tiny pebbles will orbit about each other in the same way that those larger systems do. Oh no, I think I ran out of room. I hate that so much, I'm just going to redo it. Smaller circle. How's it going out there? Y'all have been really quiet so far.
Pretty good.
Yeah. Do any of y'all have plans for the long weekend?
No. No plans.
Just study and continue binging Tiger King, I assume.
Yeah.
Or you know what? No, Tiger King was spring break, right? Everybody's done
Yeah.
watching Tiger King.
Old news.
Yeah, what a nightmare.
How's your cat doing?
Pathetic. He's in a box. He's got a cone on.
Oh,
My
no.
back hurts because I slept on the floor last night next to his cage so that he wouldn't be sad. Yeah, I mean, I'm like, I got all this camping gear. What's the point of having all this camping gear if I'm not going to use it?
There you go.
And then, yeah, all of these have the same radius r, radius r, radius r. Okay. So the first part of this is to consider the relative gravitational forces between these planets and stars, right? These three different systems. And what they're telling us is that this first one right here, that this one is unitary, right? That is to say that the amount of force being exerted by this star on this planet, by definition, this is F naught. And they're asking us to then determine the amount of gravitational force in these two systems. So maybe right off the bat, what's the answer?
The equation for it?
No, what's the answer? I assert that you should be able to read this by inspection.
Isn't B and C the same?
They are the same and they're both 4F naught.
Okay.
Why?
Because the wait. What is it right? I forgot.
We are talking about gravitation. And whenever we're asked to talk about gravitation, your brain should go immediately to Newton's universal law of gravitation, which is what?
Isn't it like G times the mass of the star in this case
Divided by
divided by r squared?
r squared.
Yeah,
And nobody's asking you to memorize that. That's right at the top of your AP test. But whenever you talk about gravity, that's not right at the surface of the planet that you're talking about. You have to use Newton's universal law of gravitation. And so what they're doing here in saying this is that, well, by definition for this system, where I have ms, mp, and r, those are the three values that you need to calculate how much force there is, this by definition is equal to F naught. So this is the mass of the planet, this is the mass of the star, and this is that r squared. If you were to actually go through and calculate what these two are, this is going to be equal to g 4 times mass of the planet, mass of the star divided by r squared. And this right here is going to be equal to g 4 times, I'm sorry, mass of the planet 4 times mass of the star divided by r squared. And in both of these cases, you just factor the 4 out to the front, you just factor the 4 out to the front. For both of those cases, the 4 comes up front. The rest of that equation is exactly what it is right here, where this has already been defined as F naught. So that tells us that these objects are going to experience 4 times the gravitational attraction to their star. Are there any questions there? No? Okay. So now here's the actual hard question. If this experiences, so this was just part 1. Part 2. If this one experiences a centripetal acceleration A sub c, how do these other two compare to this? More, less, the same, why or why not?
Equal.
Which one?
The first one and the centripetal force.
So for this one over here, this is the centripetal force.
Oh, okay.
So for object B compared to part A,
Mhm.
this has 4 times the centripetal force. Except if we want to solve for the acceleration, what equation relates for us force and acceleration?
F equals ma.
F equals ma. So all we have to do to know what the centripetal acceleration is use that equation. So here I'm going to say F equals ma, and we're trying to figure out what the acceleration is on the planet. So when we use F equals ma, we're going to use the mass of the planet. That's our object in question. So 4 times the mass of the planet times a, this is the ma in Newton's second law, is going to be equal to that thing that I defined as the force, which is this guy up here. So this is going to be g, 4 times the mass of the planet, mass of the star, then divided by r squared. And now I can solve for the acceleration. What cancels out on both sides?
Mass of the planet.
Mass of the planet cancels out. What else cancels out?
The
4 cancels out. So for object B, the centripetal acceleration is going to be equal to g, mass of the star, divided by r squared. Is this bigger than or less than what it is in part A?
The same.
It's exactly the same. And I actually gave this away yesterday. And that is to say that if you have multiple objects orbiting one other object, they all have the same orbital properties if they are the same distance. So here, it does not matter that they're both at a distance r, right? But it doesn't matter that this is a mass of m and this is a mass of 4m. Anything which is that distance r away from a star of this mass will have the same orbit. So a red paper clip here would have the same orbit. A way bigger, weird-shaped planet here would have the exact same orbit. Anything in this orbit around a star of that mass will move with the exact same velocity. As they all track around, they'll all stay the exact same distance apart as they chase each other. They will never, ever collide or interact. However, for part C, this is a pretty different scenario, and we'll see why right when we get to Newton's laws. So here, notice the force between them is the same because it's an interaction between this guy and this guy, but this is multiplied by 4. But in this case, the gravity that they feel is the same amount, but in this case, the mass of the star is multiplied by 4. And as a result, these two systems actually have pretty different equations of motion. For this final position, we'll do the same thing, right? We have 4 times the centripetal force, except what's the mass of the object going around? Here it was 4 MP. That's the mass of the planet. What about here?
MP.
Just MP. So this is to say that the mass of the planet multiplied by the acceleration is going to be equal to that force equation, g, mass of the planet, 4 times mass of the star, all divided by r squared. So now we want to compare the accelerations. Mass of the planet cancels with the mass of the planet. Acceleration is going to be equal to g times 4 times the mass of the star divided by r squared. And so this guy's acceleration is actually going to be equal to 4 times the acceleration in the other 2 cases. So this guy has the same acceleration as the planetary setup in A, but in the final one in C, this has 4 times the acceleration.
Mr. Robinson,
Mm-hmm.
I have a question for part B. To find the answer, could you have just like set the universal gravitation equation equal to centripetal force?
That's not necessary in this question because setting it equal to centripetal force would be setting it equal to mv squared over r, which will let you calculate the orbital velocity. And I'm going to talk about that at the end, but that wasn't a feature of the question.
Okay.
This question is actually answered entirely by Newton's universal law of gravitation and Newton's second law.
Okay.
So yeah, this is to say that this guy right here, these two have the same centripetal acceleration, and as a result, they have the same speed. This one, since the mass multiplier went on the middle star, is going to have 4 times the orbital acceleration. And what I'm about to say now isn't part of the question, but how much faster is this orbit than these other two? How could we figure that out? If you have 4 times the centripetal acceleration, how much faster is your orbital speed? How do you go from centripetal acceleration to speed? What's that relationship? Did it at the top of the class, did it yesterday. What relates acceleration of a circular pathway and velocity? I have all day. I'm going to ask one more time because I feel particularly alone in lecture today. What is the relationship that relates the acceleration here to the speed of the object? And if we're having issues out there, ask me a question.
Is it the radius?
It involves the radius, sure. I need an equation which relates the angular acceleration to the velocity.
V squared over R.
What is equal to v squared over r?
Centripetal acceleration.
Centripetal acceleration is equal to v squared over r for an object moving in a centripetal pathway, in a circular pathway. This is going to be what tells us how fast this object is based on how strong the force is that tugs it back to the middle. For scenario A and B, because they have the same acceleration, they're both going to have the same orbital speed. It's easy to calculate. RA square root is equal to V. This is true for both A and B, and since they have the same A, they have the same V. They are going to orbit with the exact same orbital velocity. Scenario C is different. 4 times the acceleration is going to be equal to V squared over R. I'm going to multiply both sides by R. 4AR is equal to V squared, and now I'll take the square root of both sides. 4AR is equal to V. What's the square root of 4? 2 root AR is equal to V. This 2 means that scenario C orbits twice as quickly as the other two. Twice as fast. So these two both orbit together with the exact same orbital speed, but this other one, C, orbits with double the speed. If this was like comparators of Earth and Earth-like planets, for these two, an Earth year is 365 days. For this one, it would be about half of that. It would be about 180 days to orbit it. The bigger the star, the quicker objects orbit it. So here's why I think this is an interesting question. Here's the big takeaway you want to have from it. Number one, we're talking about forces, and as a result of universal gravitation's application, these forces are the same. But because the multiplier on the force is in different positions, right? This one has a 4 times sized planet. This one has a 4 times sized star. Despite the fact that these forces are the same, this leads to a result where A and B have the same acceleration, and C is the odd one out. It's actually a really clever question. If you made the same guesses for part 1 and 2, you get it wrong, right?
If the planet is more massive, that means there's more centripetal force needed, right? To like orbit the planet?
Sure, but because gravity scales with mass, there would automatically be more centripetal force.
Okay.
So if the planet was 4 times more massive, you would need 4 times the gravitational force to keep it in orbit at that speed. But that is independently what gravity's equation happens to do. That's why all objects on Earth have the same gravitational acceleration. Everything accelerates at 9.81 because when you have F equals mg, sure, objects with more mass have more gravitational force acting on them, but when you solve for the acceleration, those masses cancel out and the accelerations are the same. That's why these two experience the same acceleration, same object that you're orbiting around, same distance. So when you divide out the masses, you get the same acceleration. But here, the mass is concentrated in the middle, so the 4 doesn't disappear when you divide by MP.
Okay, thank you.
Are there any other questions on this example?